right, man. How are you doing?
Pretty good, man.
Good job at Build, dude.
Thank you. It was a great event,
Absolutely, there was a lot of C++
sessions. A lot of C++ talk this time. I was really happy with it. Tarek started off. I was just, my talk about the journal and the Austin application.
Nice, yes.
It was really interesting. Then we had Marian with some tips about C++ CX. Then we had a super cool talk about the perf with the vectorizer.
Yeah, Radigan.
Radigan, and also AMP with Don McCready.
Yes.
And we had the book of C++ AMP coming out just at the same time, Kate Gregory. And then we had, the final closure with Herb Sutter, of course, the future of C++.
Totally.
Announcement of Milan and isocpp.org.
That's awesome. And he was on Channel 9 Live shortly after making that announcement.
Yeah, being grilled.
He was grilled.
Yes.
So they said in that article, I think it was in the Register.
On the Register,
Yeah.
Exactly. Yeah.
And they said that was one of the better sessions at Build, so that was good.
Congratulations.
And I wouldn't say that he was necessarily grilled.
No,
he was being honest.
If
you're an MFC developer, you guys aren't dropping MFC.
No, we are not.
It still gets updated, it gets fixed, whatever.
Yeah.
But, whatever, man. He answered honestly, so I don't think it was a grilling.
No.
And the Milan stuff, though, let's talk about that briefly.
Yes.
Now, this is a compiler update, and you have 6 new C++ 11 features.
Exactly.
Good for you.
On top of VS 2012.
Yes.
And you can install it, and you can, just with at the combo box, you target this new compiler toolset, and you get, variety templates, initializers list,
Great.
and other that I don't remember right now. But,
absolutely.
But that was nice. And that's our. We want to show you that we are actually working. We have the variety templates working. We have a bunch of bugs now about that. We're going to fix them. We're going to add some.
So
features.
people have been using it and giving you bugs.
Good.
Yeah. Good job, guys and girls.
Thank you. Yes.
Cool.
Yes.
So there's something we really haven't covered in Channel 9, or in any of the C++ stuff we've done, and that's profile guided optimization, which
Pogo.
is a feature not a lot of people either know about or are using. What is it?
Well, it's like the name says, adapt is profile guided optimization. So the optimizer tries to do a very good job to understand normally your code and try to optimize the best it can. But if you turn on PGO, as we call it, or Pogo, or profile guided optimization, the compiler will add some instrumentation, and basically your XE now is instrumented, and you can run this XE on some key scenarios, like startup scenario or a very important feature of your product. And then the compiler also basically gets all this information, saves a profile information that tells you, oh, you're actually in this if-then-else, you're actually taking the else part much more often. So that's the hot part. I know about that now. So then you get this information, you forget about the instrumentation, you recompile the code, and the optimizer use this information right now, and it optimizes your code very, very much, right?
Nice.
So our compiler, our front-end compiler, is optimized with PGO, like many other components in Windows or Visual Studio.
Great.
And when this PGO gets out of date, this data, we drop like 20% of perf. So it does that in some specific scenarios, right?
Of course.
So
right
that's
on,
pretty nice.
So if you have a relatively large code base,
Yes.
use this tool that you already have at your disposal.
Yeah.
Measure, man.
Exactly. Measure.
So hey, listen, speaking of PGO, why don't we go talk to the cats who own this technology,
Tzen
including
and Amit.
Tzen's amazing, man.
Yeah, Tzen is
Back-end
the
dev,
mind with back-end
rock and
dev
roll.
all the way down to the meta.
Right
He's
on.
our
And
meta
Amit's a
guy.
young and upcoming program manager, very
In that
articulate,
space.
very smart.
Very good.
Rock on. All right, we are in C++ world in compiler land. Who, please introduce yourself.
Hi, I'm Tzen. I'm the developer lead here for compiler code generator for all architectures.
Excellent.
Hi, my name is Amit Mohindra. I'm a program manager for whatever Tzen does. So that means profile guided optimization and the code generation stuff.
Excellent. So you guys do a lot of stuff, period. But today we're going to focus specifically on what you call Pogo, or profile guided optimizations. So let's jump right in here. What is it? How does it work? What's the big deal?
Okay, so profile guided optimization is basically a technology that we have owned in our team for about, since it was introduced first in VC 2005. And profile guided optimization really means is you're able to give enough data to the compiler to do a better job at optimizing your binary. So what the end result really after using this particular technology is that you have a faster and a smaller application, which is a lot of what our users want. You want an application that is smaller and that runs fast. Okay. So profile-guided optimization gets you there. A little bit of history about what profile-guided optimization really is basically it started as a team effort between Visual C++ and Microsoft Research back in the late 1990s. And around the same time, what was happening was we had this platform called Itanium that just came up. And what we saw was we could actually really exploit the characteristics of the Itanium platform by having more information about the hot paths. And that's where this technology sort of started originating. And we had about 70 odd components back in Windows that were using profile-guided optimization to create faster applications, make Windows faster. Since then, we have expanded to be about 300 components, more than 300 components across Windows, which is great.
For all architectures.
For all architectures.
For all
Today, on Win 8, for all architectures, we have more than 300 components, which make a huge performance improvements on the Win 8 we just shipped.
Yes. So let's kind of step back just a little bit.
Right.
And, you know, I'm trying to kind of piece apart the meaning of the word.
Right.
When you're saying profile guided, what is profile guidance?
Right.
What are these profiles? What's the guidance?
Okay. That's really where I actually jump onto the board and explain a little bit. So we were just talking about the fact that when you compile using cl.exe, say for example you're compiling foo.cpp and bar.cpp, code generation normally happens to the compile phase. What the compiler generates is foo.obj and bar.obj. Now since code generation is actually happening during the compile phase, we are not able to do certain optimizations that span across modules. In this case, if you're calling a function from foo into bar, we're not able to do optimizations such as inlining because we cannot see across these boundaries. So one of the things that, one of the technologies that the compiler has is called whole program optimization. So if you throw a switch called /gl, and sorry for the space problem, what we are able to do is we are able to generate foo.obj and bar.obj, but now code generation is actually happening during the link phase. What that allows for us to do is basically see across these modules. And when you see across these modules, you're able to do better optimizations. And now we can do a function call into bar, we can inline into foo, which basically makes things faster. And so that's basically an example of how this technology works. Since we have more information about it, we're able to do a better job. So how does Pogo utilize this technology, and what's the process really that's involved in it? So what happens is there are three phases in profile guided optimization. One is, first is the instrument phase. So you take your application, right? You take your source files, and you give it to the compiler, right? Compiler, and you throw that /gl switch. Behind the scenes, we are generating a call graph information, we are generating a control flow graph, and what we do is we generate an instrumented binary in this case. So you have an instrumented binary. So you have instrumented your application. This is how we can now collect more information about your user scenario. The second step is train. So the most important user scenarios that are performance critical, you take those scenarios, so there can be multiple scenarios, and you run these on the instrumented binary that you have. Right? And what comes out in the process is a bunch of traces, for that matter. These are traces or profiles that you get. Now, why are these profiles important? And the last step in the process is called optimize. Now that you have actually collected these traces. These traces are a way to tell the compiler that these are the most important scenarios, so do the best job you can. So you take these traces and you feed it to the compiler again. And the output is basically smaller and faster application. Now, some might be thinking that these are steps, I mean 3 steps, it's really hard to do. But one thing to note is that this collection of traces does not have to happen always. You can collect these traces, check them into source control, and keep reusing them to basically make your application smaller and faster. And you don't have to regenerate them always, unless the code has drastically changed. You can keep reusing them. And you'll get significant performance improvements because of that.
So why drastically change? I mean, what if you've made changes to a class?
Right.
I mean,
So, yeah, that's a perfect question. If the changes are not significant enough, you don't have to regenerate these traces.
So what is that? So the question I have is like, what does not significant enough mean?
Like for example, you changed basically how a branch works inside of a function.
Okay.
Right. And if basically that is not in your hot path, then we will not discount the traces that you've already collected. In case that that does lie in your hot path, we will discount the traces, but the rest of the program, the hot paths that you already generated, the counts are still valid for those. So if you just change a simple function, you might not want to regenerate the traces.
Okay.
But if you change the whole implementation,
sure, understood.
So actually, so there will be a number reported by compiler show the percentage of profile function which are still good. So when this number drops to a significant percentage, maybe it's a time for you to recalculate the count.
Sure,
So,
understood.
and that's outputted
There will be
inside
output
Visual Studio.
in the Visual Studio.
Yeah.
Right.
Great.
So
I'm actually going to move over to 10 and explain to you exactly what happens during instrumentation phase.
Great.
And what happens during optimization.
Perfect.
okay. Thank you.
You can do it.
So first, again, a little history about the VCCompile. The backend we are using today has been shipped 7 releases since 1997
Okay.
on about 5 or 6 different architectures. So this is actually pretty mature and advanced backend code generator. So for a mature and advanced code generator like this, ultimately the code quality will be determined by the amount of compiler information, the amount of information compiler can see. The more information we get, the better code we generate. So this just kind of echo what Amit just said, whole program optimization. Right? With LTCG, we see the entire applications. We see every function. We see the relationship between functions. And we can analyze and also perform optimization across function boundary, as well as, most importantly, source code file boundary. So you'll say, okay, that's good. So what do we miss? So what we miss is that the best we can do with compiler LTCG is statically analyze your source code. There are a lot of information which can only determine during runtime that compiler like to know but will never be able to get without another technology, which is what brings us to the profiling Pogo optimizations.
Okay.
Okay, let's show this by a few simple examples. If A less than B, we call bar A errors, do something else. Okay. Okay, this is big enough, right?
Sure.
Compiler doesn't know how likely A less than B is. And many times, many situations, there's no way compiler could conclude how likely this is because A could come in from an input file or derived from some input data. So without extra technology, like we talked about Pogo, creating account, we will never be able to know how likely this block will be executed. So what's good about this? By knowing this block will be executed hard, compiler can be more aggressive to inline it, right? Inline this block.
Okay.
And of course, it will generate a better code. So this is one example. Another example, okay, here, a for loop. Again, for example, we call bar. Compiler like to know how often this execution, this block inside the loop is executed during the runtime. Right? By knowing that, we can be more aggressive to inlining. We can do loop enrolling. We enroll the loop, or we can even do software pipelining.
Okay.
So by knowing this number, we can be much more aggressive on optimizations. One more example. Okay. Let's erase this. We call switch I case 1 do something of case 2. So compiler would like to know what is the I value most likely, right? If we know I is mostly equal to a specific value 1 or 2, we can turn this case into a if else to avoid the indirect jump table overhead.
I see.
And to shortcut the execution. So you can see this can improve the runtime performance. So this is a very typical example. This is why the information compiler like to know, but without Pogo, we'll never be able to conclude the information.
Okay.
So after this, I want to show, by combining the 3 examples we just showed, I want to show how compiler can exactly do the instrumentation on your source code by this example here.
Great.
Okay, we prepare. This is a combination of the 3 examples I just showed. A loop with if statements, call bar, and else, we do switch. All right, so this is a very simple, typical program. The control flow graph corresponding to this function is shown right here. So in this control flow graph, what we have on the node is the basic block, the instruction we execute. The edge represents the control if flow. So if you remember the code, we initialize I equals 0 at the beginning of the loop, and then inside the loop, the first statement is if A less than B, yes, go to call bar, otherwise switch statement. And then these 2 blocks merge at the end of the loop, and I increment and check the boundary going back to the top of the loop. So this is what we call control flow graph. We use a lot in the compiler technology to analyze your program. Now, as I said, the purpose is we have to collect the count for each block, each edge. So we know how many times this block is executed, how often this path got taken, right? A simple way is we can instrument a probe on every block. But that is very naive. That would not be very effective. Right? So what the technology we use is called spanning tree. We apply the technology we call what is the minimum spanning tree mean on this control flow graph is the tree which can connect every block. But because it's a tree, they should not have a back edge. They should not have a cross edge. Right? I want to show one possibility of the minimum spanning tree in this control flow graph by the red light. Okay, here we take this one, take this, this. Now, do we have all the nodes connected? No, here not. So another edge is this. So the red edge here is called the minimum spanning tree. What compiler will do is we will put the probe on the edge, which is not on the minimum spanning tree.
Okay.
Okay. Now again, I should define what the probe is.
Yes.
Okay, I should define the probe. We have two types of profiling probes. One is called counter probe.
Okay.
The other one is called value probe.
Okay.
The counter probe is a probe to count the number of times a specific code path got visited.
Okay.
So for example, how many times this loop got visited. So we can put a probe here, counter probe, and it's just record the number of how many times this loop got visited. Another probe, what we call is called value probe. We have to know the value, exactly what the value of I here. So we can put a value probe for I, for example. With this value probe, we will construct the histogram of variable I. So how many times I come in 1 or 2? Mm-hmm. Okay, this will record all the value. So this is two kind of probe we will generate. And now let's go back to this control flow graph. We like to collect the count for each block, but we don't want to put a counter probe on every block. Mm-hmm. The technology we do again is we find the minimum spanning tree, and what we need is put the probe on the edge which is not covered by the minimum spanning tree. In this example, we would have a probe here. Could have a probe here, and to cover this edge.
Okay.
Then we have another probe here to cover another edge, and of course we will need an entry probe here, entry probe at top of the function. So totally we will have 3 counter probe for this function. With these 3 probe, compiler can figure out all the count of every block by propagating the probe and by summation or subtraction across the control flow to figure out the count for every edge and block. So also there will be a value probe, as we say in the switch example here. There will be a value probe to collect the count for this switch.
Okay.
So totally 4 probes will be generated for this function foo. Okay. Again, probe is the piece of code we inject into your program. That code will collect the count and store in your memory space, and at the end of the execution will be write into the database. The database is the what in Amit, the diagram here, the database.
Okay.
So to do that, compiler will also allocate the space for each probe. In this case, there will be 4 counter or address space allocated for corresponding for each probe.
Understood.
So this space will be in your binary memory space. In our technology, we call the data set. All right. So so you maybe wonder, but the behavior of this function could be extensively different. The behavior of the function called by one caller, call site, could be extensively different than when it is called by different function. Mm-hmm. So, so what I mean is, for example, you let's bring this flow graph one level up. For that, what we call is called call graph. So this is a flow graph for foo, right?
Sure.
But foo is calling foo.
So what calls foo?
Right.
Call graph.
Right. That's in the call graph. When you create the call graph. So assuming this is a very simple program, you have name here, which call A call B, and then A and B call foo. Of course, because foo call bar, right? So there will be a bar here. Now, it's very possible that when the execution path is coming from foo, the hot path is this. Go this way. Mm-hmm. Okay, let's make a win. Assuming execution coming from foo. and this is the half pass from green. But when this execution coming from B, the black pass is already black. Okay, let's use red. The red pass, the half pass is going this way. So this is what we call the count is determined by the call path. So technology Pogo use is called call graph path profiling. So we like to collect the count which is specific to each path. So by doing this, what we do is Pogo will analyze this call graph. Okay, this simple call graph, and we will do a bottom-up traversal and identify all the potential call paths. For example, you have this path and this path. And then we assign a unique path ID for each path.
Okay.
So assume this is the green one is path ID 1, the red one is path ID 2. And then with this path ID, that will be passed from the call side into the foo by a special calling convention. So the path ID 1 will be passed to foo and get into the foo here. So when it get into the foo, we know they were coming from 1. Right?
Okay.
We're coming from 1. So we will, this entry probe will adjust all the probe to point to one data set that is specifically for this path. So when it is coming from B, right, path ID is 2. The entry probe knows, oh, we are coming from different paths. That will create a separate data set corresponding to the grid path. And again, there will be 4 space allocated for 4 probe of this function.
Okay.
And the probe will, the data collected will be stored into this data set. So with this is a technology what we call is unique technology used by our VC profiling, with path profiling technology. With this, we can do a better optimizations because we know exactly which path you come in, and we do the optimization accordingly.
Nice. Excellent.
So I guess another thing, I'll just jump in a little bit here. The data sets actually help understand what are the counts. So we can actually make decisions such as Tzen was mentioning earlier, whether bar needs to get inlined into A, or whether bar will get inlined into B. Because we have information specific to the paths based on the profile IDs, we can make certain decisions based on that particular information.
So that brings us to what your original question. What this information, all this profile information can do for compiler.
Yes.
So that's what we call the PGO in the explained very early.
Yeah.
Profile guided optimization.
Got it.
How it guided. So with this information, right, we have a count for each block, and we know this count belongs to this path. Right? How we do optimizations. So there are probably hundreds of different optimizations today we perform in the compiler backend. Almost all of them, I would not say all of them, most of them can utilize the profile count to do a better job, to do a better code generation. But among all of these, I would say the major profile guided optimization we are writing right here.
Okay.
Okay. I will quickly go through each one, and the first is the inliner. Okay, you know the inliner.
Yes, we all know the
Everybody
inliner.
inliner.
You better know the inliner.
So why inliner is important? In my opinion, inliner is probably the most crucial optimization in compiler backend, regardless with or without Pogo. Okay, what's the benefit of inliner? You know? Because inliner can, with inliner you can eliminate the calling convention overhead. You don't have to pass and receive arguments. By inlining a function, you can turn a global variable or input argument into a constant. And then, because the constant is possible, we can further remove a branch or remove a compare. With inlining, we expose more code again, more information to downstream optimizations. So they see more code, they can do a better decision, can make a better decision for optimizations. So inline is so important, but on the other hand, compiler has to be very careful not to overly aggressive inlining. So what's the problem? If you overly aggressive with the inlining, you could increase the core size, and that could result a negative performance impact because larger working set, right? You will miss TLB because you could resolve a poor cache locality. So that's what inliner is so important. So what Pogo information provided allow inliner to be more precisely make a right decision at the right good point, and that is based on the path specific information.
Yes.
And then we do that in a recursive manner. We do the inline decision in a recursive manner. I want to show this example again about inline, what Amit just said. Here is the, are you looking into here?
Yeah.
Okay. This, assuming we decide full inline into A, also decide full inline into B. So after full inline into A, you will see now the bar will call by A, right? So we need to make another decision.
Okay.
Should we inline bar into A? Right? Without path specific information, it's hard. But with path specific information, here we know the data set for full is this data set. This data set is corresponding to this green path. So we know when the full inline into A, we know the bar will also very hot in A. So we can decide with inliner. On the other hand, when we inline full into B, the red path, and B also called bar, right?
Yeah.
But this time, the hot path is here. So we will not inline bar into B because it's pretty much a dead code in B. So that is the power of the Pogo inliner.
Interesting.
Inliner is a key factor actually, is the number one key factor for Pogo to achieve, again, smaller and faster code.
Yeah, because you're actually removing code
Now,
paths.
Right. We are eliminating the need of the inliner on a code path.
Yeah.
And that achieve smaller code.
Smaller code is good.
And I think one of the advantages of the inliner is also that it's intelligent, and
Sounds like it.
and we don't do aggressive inlining. We don't inline everything.
Okay.
Because we have information from the profile that you collected, we will only inline specific parts. Exactly as Tzen said, bar will not get inlined into A, will not get inlined into B. So we are not overly aggressively inlining and not increasing the code size too much, but still giving you the performance benefits.
Absolutely.
So-
And the data that you're basing these decisions on is real data
Exactly.
that lives in the data sets that you've already gone. That was your first part of your instrumentation and analysis.
Exactly.
Yeah.
Exactly.
So it's a much more intelligent way to inline
Exactly.
based
Exactly.
on real code paths and real hot and cold.
Right.
Very nice. Okay.
Okay, that's
So if I understand it, everybody else out there understood it several minutes ago.
right.
All right.
Good. Because that is the key optimization for Pogo.
Sure.
Good inline. Okay, another optimization. Okay, sorry, bring back to the list. We call, okay, I want to say size and speed selection.
Okay.
Now, if you are a VCCompile user, of course, you know there's a choice to optimize your function for size or for speed. So why we provide this choice? Because for size, compiler will be more aggressively, which could at the expense of increase the core size. For example, again, inline is one. Another one is a loop enroller, right? You want to speed out this loop by enrolling this loop at the expense of the increase the size. Also, like we have a tail duplication. Okay, we can duplicate the code to avoid a jump. However, at the expense of the code size. Also, like some instruction selection. You have some instruction is faster, however, it's bigger. Some instruction. So the trade-off between size and the speed is also very important for us to achieve smaller and faster code. We don't want to compile a function that optimize for size we don't want to compile a code or depth function optimized for speed, because it never been executed. It hardly executed.
Sure.
There's no point to compare those code functions with speed for speed. So Pogo make a good decision based on the information we collect. Okay, as the show we just show. And typically, we would expect the number of functions would be optimized for size is about single-digit percentage of all your function. So if you have 100 functions, you better not to optimize for speed for 90 functions, right? If it's not, we like to optimize for top few functions. So Pogo, at the end of compilation, Pogo will report a percentage of the function optimized for speed.
Nice.
In our experience, the good number, what the good number means is your training set is good. Is representing a good scenario. It's single digits, 3%, 5%, and that will significantly reduce your code size, and also maintain all the performance we want to optimize for.
Great.
And this data is available in Visual Studio when you're doing optimization?
Yes, it will show you at the end of compilation. We'll show you the percentage.
Yeah.
And if you see your number of functions optimized for speed is only 0.1%, well, you are undertrained. You need to improve your training scenarios.
Okay.
So that's size and speed. Next optimization I want to say is called block layout. Okay. Let's go back to our previous example. If A less than B, do something bar, call bar, else do something here. Again, we say the control flow graph for this function is like this. We'll have a block A, if call go to here, else go to here, and then you merge. So this is a control flow graph of this piece of code. Then, so without Pogo information, how are you going to position this block? So naturally, we call topological order. It is we do 1 first, and then do 2, and then do 3, and do 4, right? We are going to put your code in this order without Pogo. But what the problem of this is, assuming this is the hard path. Again, we have Pogo information. We know this is the hard path. It always take this path. So what the execution will be, go 1, and then you jump to 4, right? So what the problem of this? You could suffer branch misprediction, right? You mispredicted, and you have to flush the pipeline, right? You could resolve a poor cache locality because now you involve 2 cache lines rather than 1 cache line. Okay, so by knowing this is hard path, Pogo will order your block better. We can do, in addition to 1, 2, 3, 4, we will do 1, 2, 4, 3. Right? The execution will be straightforward. We will avoid the branch misprediction and have a better cache locality.
Okay.
And furthermore, another optimization, what we call is code separation. Code separation. What we mean by this is, assuming this is more than just code, it is totally dead. What I mean by dead is it's not really dead. It's never been executed. We call runtime dead.
Okay.
We will separate this function into 2 pieces. The function will be separate, become live part and a dead part. And dead part will put away, far, far away at any of your binary image. Okay. So what is advantage of that is that we reduce the working set. You have the better cache behavior. And overall, you improve the performance.
Great.
Of course, there's the whole list of optimization. We will not be able to go through the detail for each of that. Here, I like to just quickly go through this. Another one is function layout. Okay, the block layout we do on the flow graph, we do thing on the core graph at the function level. Okay, so after enough decision has been made, we know the calling relationship between functions. So we will put those functions, they call each other together into the same page as close as possible. Again, the purpose is reduce the working set, avoid page fault, and better cache locality. So that's the function layout. And the switch table expansion, I already mentioned in early example. Right? You can do a shortcut for a specific case by the linear.
The hot case.
Hot case.
The cold
by
case.
If, yeah, exactly. Good. Another one. This is what a virtual call.
Virtual calls.
Virtual call. We are inlining. So what we mean is that, remember we talked about the value probe. Value probe for the switch.
Yep. The probe.
The probe can collect the value of a variable.
Okay.
So we will collect the value of a function pointer. Right? A function pointer. Without Pogo, this function call is always indirect call or virtual call. You know C++, right? So the virtual call is an indirect call. You do the binding during runtime, so it is expensive.
Sure.
And even more important is, because it's virtual call, it's indirect call, we cannot do inlining. Okay. So with Pogo, with value profiling, we collect the value of this function pointer. And this pointer would, with that we know, okay, most likely this function pointer will point to function foo, for example. Right? The semantic of function pointer call x, y, star, right? Is a function pointer. Okay, if we know this p is always assigned the value of address of foo, we can turn this into a direct call to foo.
Yes.
And then we can further inline foo.
Great.
That we will call speculative inlining.
Okay.
And other than that, we also have loop unrolling. You know this, right? We know this loop is hard. We unroll it more aggressively. And Regis allocation. Okay, what is the point of Regis allocation? Let's give this example again. If we know this is a hard pass, when we are under high Regis pressure, we need to spill some register, which is expensive. We can choose spill here rather than here. Okay, because it's hardly executed here. So we can improve the effectiveness of Regis allocation. And also data separation. Like we separate the code, we can put the data which is never been touched in the far away of your image. And then, okay, I don't mention this one. You will like it. The partial inlining.
Okay.
You know the inlining, right?
Yes.
The inlining function.
Okay.
So what is partial inlining? Partial inlining is we inline a part of your function. Why is that? Because your function is too big. You will increase the code size. So if I know only the top part of your function is hard, compiler can just inline a small part of your function into caller, which can improve performance in speed.
Yes.
Without inline the remaining part of your function.
Great.
And achieve smaller code.
Cool.
So with Pogo, we can do that too.
Now, in that case, if your function, you have to be careful because if the code that you remove from the function relies on other pieces of the function, right? Like changing the value of variables or relying on some kind of state.
That's
somewhere.
a very good question.
Yeah.
So do partial inlining actually have two paths. We will check if, how about let's give this example. This is a good example. Okay. Assume this is the function. And this function is pretty big. Okay, pretty big. And we have a few instructions here, like A equals A plus something, B times whatever. And we know this is hard pass. And the caller of this function will just inline this part. And
Yeah, exactly.
we will inline this part A into B, and still inside the caller, we will have this. Okay, if A less than B, we do this plus B times blah blah blah. Else, guess what we do? We call this function again.
Great.
So this is in the caller. So we only inline this one, into the caller.
So it limits the number of times you actually have to call a function from a different caller.
Exactly.
Which certainly will affect performance.
Yes. And without increasing the size of the caller.
Yes.
Because the big part is live in the calling, not inline into the caller.
Now, when you do these replacements, when you do the partial inlining, in general, you actually shrink the size of the inlined code. Do you understand what I'm asking? So, function X, you take a chunk of the code inside of function X, inline it into a caller, Y.
Small
You actually remove that code from the...
Oh, actually not. This
Okay.
code
So it's not making code
No.
smaller.
Yeah, but this function hardly will be called in the runtime
I understand.
anyway.
So you're going to move that way into the back.
The function will not be involved.
Yeah,
Understood.
It doesn't make it smaller, but what it does is the amount of code that you need, since it is already inlined, you don't have to actually cache the whole function now, second function,
Yes.
because it's so big, and it it improves for the amount of code pages that we have to bring in,
Sure.
and lesser page faults because of that, and
Great.
faster code.
Now, do you see a lot of people actually, in today's day and age, are we seeing people with giant functions?
Mhm.
Are you seeing a lot of giant functions in the field,
This
in reality?
partial inlining feature is specifically requested by SQL Server.
Aha! The
For
SQL
example.
guys like big functions.
Actually, this is not big function.
Just kidding.
The
Right.
shortcut on the top of the function is very typical. Like if error number, immediately return, right? How often you see the code like this?
Yeah,
If something, you do something, immediately
Yeah.
return.
sure.
And sometimes that pass is hard. So this is a pretty typical programming style.
Sure. And for something like SQL Server, which is all about extreme efficiency,
Mhm.
and
We also actually want to mention
sure.
how the gain the Pogo can bring to you.
Okay, what is the gain?
Okay,
So-
I will let Amit talk about the result.
I'm all
Bring
about.
the PM back in.
You need to bring the PM
the value
back.
proposition.
This is all good technology, right? What is the gain? What are my customers getting is really the question I ask. And Intense worked on this technology for a very long time. Well, we just wanted to give a few examples and basically say how we bring it to, how is it important to our customers out there.
Mhm.
So to give actually a very brief example is like we have a DLL called MSHTML that ships in Windows, and it's mainly driven by IE specific scenarios, right? It's a pretty huge DLL, and in terms of size. So when you do LTCG, which is link time code generation, we referred to this a lot while we were talking about the technology. The code size that you get, because after it's done inlining and everything, is about 19 million lines of code.
Bytes.
Right. But
19 million bytes.
bytes.
19
million.
megabytes.
Megabytes, thank you.
19 megabytes. Yeah.
19
Did I say
megabytes.
19 megabytes.
Well, that's 19 million bytes.
Oh yeah, right. So
When you
that
do-
MSHTML is a huge component.
Yeah, it's big.
When you do PGO, the code size drastically reduces
Nice.
to 16 megabytes, which is huge. Like, I mean, we are doing intelligent inlining to get that reduced size. So the goal always for PGO is smaller and faster code. Remember we talked about the fact that we do function level layout, block layout, dead code separation. What that results is in the live code that is live is 2.4 megabytes. So the code size that is actually active is that less. So this reduces smaller code, and this results in faster code. Smaller code means smaller working set.
Understood.
So that is huge for us and for our customers even. Now, like if you look at the inline instances, if you go to link time code generation and look at inline instances for LTCG, in this source space we have about 930,000 instances.
Yeah. Yes.
Right? And when we go back, when we do PGO, so this is basically when we ran LTCG, how many instances of the functions we inlined. Now this attributes to code size increase. When you do PGO, since we have more information and we are more intelligent, with profile guided optimization, we reduce it about to half, 438,000. So
Nice.
reduced code size. So smaller and faster code is the mantra. And we want to bring this, so people might be thinking, you're showing me MS HTML, that's not my regular scenario. I mean, I have smaller DLLs. I mean, what do I gain from it, right? If we do that comparison, right? So our heuristics are based on our, like we have owned this technology for years. Anything that is greater than 1 megabytes in size can expect to see greater than 10% improvements using PG.
Now that's including statically linked libraries.
No, that's on top of LTCG.
Okay.
This is on top of LTCG.
On top of LTCG. Okay.
Right.
Just asking.
So you see more than 10%, and we actually have like VC. In that we have components such as backend and frontend. They're not huge. They're about 1 megabits in size.
Okay.
And we see double-digit performance improvement, which is great.
Sure.
And C# too. Right?
And C#.
Sure.
And CLR, all self use Pogo.
Sure. Well, when the CLR is a C++ application,
Yes.
and,
Yes.
and so they compile it with your compiler.
Yes.
C#, of course, has its own compiler.
Not yet. I think previous version was using C.
Before it was it's still using C++.
Yeah.
The next version
This
is
version
going to
will be
use
by
C#.
itself.
But that's independent. They have similar sort of things. I mean, background, this is compiler technology that's certainly advanced in this case, but it's not like new. And what I mean by that is lots of compilers implement this sort of
Exactly.
Yes.
hot path, code path, even tree shaking, stuff like that. I mean, so this is great. But listen, one thing though, Mr. PM, Mr.
Yes.
Mr. Businessman. So, smaller and faster code. Nothing comes for free.
Yeah.
So the cost obviously is going to be compile time, or analysis. When you do the whack GL,
Right.
it means all right. I'm going to go out, get some coffee, get some tea. Do you understand what I'm saying? Nothing comes for free. It can't come for free.
It is not for free.
So what are some of the other costs I need to think about?
So I think the compile times are larger. For sure, you've talked about that.
Yeah.
And we have tried. I mean, we are continuously investing in improving that.
Sure, no.
In the previous release, we made the compiler multi-threaded, so the link times are hopefully reduced
Speed by 2x.
by 2x.
Nice.
which is-
More than 2x.
Nice.
So
nice.
that is huge, and we are continuously investing in getting the link times really low.
Okay, so that was the easy scenario, easy question. In other words, what are some of the other trade-offs?
So the trade-offs are really the complex. I mean, to a certain extent, I think we have to go out and reach out to folks and let them know the value of profile-guided optimization.
Yes.
And there is a notion that it is complex in terms of the 3 steps that are involved. Like the cost is really you have to instrument, you have to profile it, and then you have to optimize it.
Yes.
The important thing to know though is that you don't always have to follow those 3 steps. You can reuse most of the counts. In which case, once you have the profiles, you can just reuse them and optimize your binary. Even if in the case that you're maybe adding some more, you just have to add new scenarios. You can still reuse the counts that are valid.
Sure.
So the cost is the process, but the process is not. I mean, it is reusable. So invest once.
Yeah.
And get the performance advantage.
And so to use PM terminology, which is something that good old the developer here wouldn't use, the ROI here, right?
Yes.
The return on investment is, think about it. The investment isn't that big of a deal. When you do optimization, when you're a developer, when you're an engineer, you're always measuring. You're always running, measuring, optimizing, measuring. You have to do that. You have to instrument.
Right.
Things just don't come automatically because you press build.
Right.
But in this case, it gets you really far down the road. I still, as a developer, need to think through. I mean, for example, in Visual C++, I know that unless I guess I can turn it off, but I mean, I'm going to get auto vectorization for free, which is going to do a bunch of stuff ahead of your analysis, right?
Yeah.
So I'm going to be giving you code that's already been auto vectorized.
Yeah.
And so you're going to see you're going to understand what to do with that. The moral of my story is there's a lot of machinery and complexity. The developer still can do things to help Pogo do the best it can.
Right. it's not just limited to the optimizations that we already have.
Yeah.
You can tell us more. Tell us more and we'll give you more.
Great.
So the return on investment is huge if you're ready to invest. Right?
Hey, man.
So invest more and you'll get
Let
more.
me ask you guys something. I mean, you guys have a lot of internal customers. I mean, you mentioned Windows, you mentioned SQL Server. I would imagine there's Windows Server, there's a CLR team, there's a Visual Studio team. And name any of our products, they're using your compiler, Exchange, Office. So, are all of them using Pogo?
No. So that's number one concern about Pogo is, for example, it has to be LTCG.
Ah.
So Office.
So explain to us why that's a problem, or why that matters.
What?
For people.
For me, it's
Yeah.
not a problem.
Yeah.
But for example, for Office, it's a problem
Ah.
because LTCG means you have to rebuild the whole application.
Ah.
You have to recompile every function, even you only change one function. So this is what the next project we are thinking about is we want to provide, we call incremental LTCG. So when you only touch a few functions, we don't have to recompile the whole thing.
Yes.
So that we hope we will come up something for this.
I hope
in
so.
the future.
Well, you should be able to.
Yeah, but that is not a small work. It's a lot of work to
I'm
make
sure.
that happen. So LTCG is one kind of blocker for the adoption of Pogo. Well, to me, it's not a blocker, but for some like Office.
So if you have a gigantic code base
Exactly.
with a lot of libraries that you're going to be linking in,
Right.
and of course Office is a gigantic code base,
Right.
Obviously that's going to be an issue. I don't want to have to, when
Right.
one thing changes, I don't want to
Right.
recompile everything.
So-
But there's a lot of work going on in that area generally across the company. But speak. I'm sorry to interrupt you.
Another one, okay, LTCG is one, right? So
Yeah.
we are thinking about this. We want to work on incremental LTCG. Another one is we call usability. Usability is sometimes not exactly the problem for internal customers because all application like
We have
Windows,
matured problems.
SQL, and all the CLR application, we like to get all the performance we can get. Okay, regardless of cost, I would say. So usability is more about external customers. Okay, we like to provide a better user interface in our IDE. You know,
So
to make it easier to do the three-step
And-
process Amy just mentioned.
And
right?
Absolutely.
why it is important, I was actually going to mention that we actually ran a survey very recently to understand from our customers as to what the problems are. And we hope this channel line can actually trigger a conversation where we can actually get to know more.
Yeah.
But what we figured out with Pogo was it's sort of a black box today. There is no feedback loop that we are completing with the users as to what we were trying to do and what we thought were hot paths and what we thought were things that we inlined. Maybe those are things that you didn't want to. So people don't have this holistic idea whether the training set that I just created is good enough. So we are trying to come up with ideas of how we can solve that for our external customers. It's still in the ideation phase, and that's what we are thinking, that if we complete that feedback loop, we can get people to know more about it and solve some of the, apart from some ID related workflow issues that we can improve to reduce the number of steps the person has to go through.
Well, I mean, in some sense, if you think about like the modern generation of applications in the real world, which are mobile applications running on devices with constrained resources, or they're tablet applications, which is the same thing. So let's look at Windows 8 application development, for example. People are they're using your compiler for Windows 8 store apps as well. In some sense, you definitely want to have smaller, faster code.
Exactly, yeah.
And if you could do sort of a scenario-based thing, like here's some C++ code, an app that I'm writing, and I'm bringing over to Windows Phone 8, which of course now supports native code at the component level. Smaller, faster, please.
So
please.
exactly, and I think that's one of the things on our plate is to bring this technology forward to these modern applications, and that's like Windows 8, for example, the new type of applications that we have. Smaller, faster code is absolutely what people want because you don't have all the resources available to you at every time, right?
Yeah.
You want to be very judicious about what you're using, If you have smaller and faster, if you have smaller code,
Yeah.
that's better.
And I think compile time, the compile time comment that I made is sort of orthogonal, or a better word would be, doesn't really matter, because at the end of the day, it might take, developers by design are supposed to, this is from a colleague, a friend, Mike Lee, in an interview that I did, but developers are the ones that take the pain, so the customers don't. So if it's going to take my application 10% longer to compile and to do this analysis, then so be it, because at the end of the day, the user is going to have a very fast app. It's not going to eat a lot of resources. It's not going to take up a lot of working set, that kind of stuff.
Yeah.
That's how we need to think through this. So, you know, it's interesting to me because I do wonder how many people in the real world are using this technology. Do you have a sense?
Okay.
Now, I'm not talking about internally.
Okay. That's, again, I think our problem is we need to make it easy to use for Pogo in the next release, so that people can adapt. Today, the number we got, I think.
I don't need the real numbers, but is it a?
Well, it's not very encouraging.
Okay.
We think there is more. I mean, there's a lot of value that Pogo provides, and folks should use it. There are certain problems, as Tzen is just mentioning, that we want to solve.
You want to make it more visual, right?
Yeah.
In the
Right.
IDE.
That's one of the purposes of this interview is, right?
Yes.
We like to know the value of Pogo. But I do can give an example. For example, SAP, you know, SAP program is huge, it's big.
Yeah.
They gain a huge performance gain with Pogo.
Excellent.
Okay, you know, the application like that will definitely adapt Pogo.
Great.
And also, I think Pogo is very valuable for the CPU intensive applications. I do believe Pogo can help game developer because it is a CPU intensive code, a lot of loop and hard trace. And of course, as we said, the larger application will benefit more for Pogo. You know, the larger you get, the more gain you will get.
Makes sense.
But one thing I also want to mention is the incremental profiling, for example. Right? We talk about when incremental LTCG, you modify one function, you have to recompile the whole thing. The same thing, the concept of called incremental profiling. When one of the function got changed by one line, today with Pogo we have to throw away all the information for this function. So it's another area we want to improve. So that the profile data you collected can last longer.
Okay.
The percentage can be maintained high with a longer time. So there are quite a lot of area we want to improve. For example, again, like today we don't have the concept of the phase. Okay, when you have your application bring up, sometimes you have the phase called the startup phase, and then get into the steady state phase, and then or shutdown phase, right? By collecting phase specific information, Pogo can arrange or code better based on the phase information you run through. So that's what we are going to provide multi-phase in PGD file in our next release. So with that, you can have the code running faster in your startup, and then also have a good locality for the code in your steady state or whatever number of phases you have. So there's another improvement. We are working on that.
Great. Excellent. So thank you for your time and for teaching us how this stuff works. I'm sure the Niners will have more questions, and I would recommend people out there with larger code bases to use this.
Yes.
And what else? What else do you want?
Anything greater than 1 MB, go try it, and you'll get return of investment.
Excellent.
All right.
Nice meeting you guys.
Okay,
right.
thank you.
Thanks,
Cheers.
Thanks, Charles.
That was killer, man. It's really nice to meet Tzen.
Tzen, veteran
And also Amit.
on the C++ team. You know,
So how
Tzen
long has he been on the C++ team? Forever.
Forever, probably
Yeah,
15 years. Yeah, something
Totally.
like that. Yeah, so.
So in the
definitely,
interview, he
down
talked
to the
about
metal,
like the iterations you guys have done since '97, and how mature the technology
yes, the
is now.
technologies. Yeah, like I said, we use it in major products, right?
Right
So,
on. So
absolutely.
cool. So you guys use it,
Yeah.
abuse it, and give feedback.
Let us know what you think about, how you can use it, find it easy, find it hard.
Cool. So I also wanted to throw out a little something for my native brothers out there
Right.
who were working on the Barnes & Noble engine
Ooh, cool,
right?
Yes.
Well, so
It's
the
an
Barnes
app
&
I
Noble
like.
app, the Nook reader is now available. It's V1.
Yeah.
Go to Windows Store, download it, buy books. It's a really nice reader. The C++ part of it is the engine, and so shout out to Jim Lester and Mark Boulos for the great work they've done.
Cool.
And the cool thing about this app is that it's C++ underneath,
C#.
C#.
To do the XAML. So
Do the XAML.
You can reuse it on the phone as well.
Exactly. So they
Nice.
want to be able to move it over to the phone.
Beautiful.
Which we're not making an announcement or anything, but you
Right.
can kind of put the pieces
See
together.
the,
And the phone doesn't support XAML with C++
Right.
underneath. So come on, man. Where's Peter Torg? Let's go, bro. But anyway, so that's that. So I
That's
wanted
it.
to do a big shout out. Download it, play with it. It's got a lot of native code in it actually, and it's a V1,
Yeah.
just like the platform's a V1. So
But the apps are coming up.
they're coming
That's
up.
good.
It's a good first start.
Yeah.
So I'm happy to be
Yeah,
involved with that.
We have STL,
Yes.
the new episode online,
Yeah.
beloved by
He is
by our
beloved.
viewers. Super smart kid.
He's a very smart kid. Now listen, I also wanted to say Herb Sutter. You mentioned Herb Sutter as the future of C++.
Yes.
Well, Herb, I heard you talking to me when you were giving that presentation, and you had asked questions about, hey, Charles, should we do another Going Native? I would say my answer would be absolutely we should do another Going Native. And I think what we should do is figure out when the date's going to be, because I think it's going to happen in 2013. This is not an announcement, of course.
No, it's not.
But we got some great ideas, man.
Good.
So I think it was a
looking
total
forward.
success
Was a
last
great
year.
success.
So-
People loved it. We had a great speakers.
Rock and
great
roll.
speakers. He did a great job. Yeah.
Cool, man.
Cool.
And for anybody out there wondering, like, any of this leadership stuff they've heard about, is that going to impact the Renaissance? No.
C++ rocks, man.
Rock and roll.